I now have a post-processor that should work, but there are still several uncertainties about the robot's motion. Some issues may have been resolved correctly, while other tests produced contradictory results that still need verification. This is where first-hand testing of the robot could answer some of the uncertainties. I also don't know if what I've been doing is correct or not. I could not find downloadable meshes for the Kawasaki FS45N. RobotDK provides a .robot file, but does not expose the meshes, and its AS language output is locked behind a compiler. I therefore modeled the robot myself using the installation and connection manual with RobotDK's geometry as a visual reference. The meshes are sufficiently accurate for simulation, while the critical dimensions for the robot's motion came from the manual. The next problem is that the robot's plugin does not support Kawasaki. The plugin's discussion page suggests using the XML of an existing robot as a template. However, changing the manufacturer to Kawasaki is not possible. If the XML contains a manufacturer outside the plugin supported list, it immediately returns an error. I therefore had to identify the robot as a supported manufacturer such as ABB or KUKA. Another concern is that the XML only accepts 2 DH parameters per joint, A and D. This may be a problem by itself, since the plugin could be applying additional manufacturer-specific conventions internally. However, those settings are neither visible nor adjustable, so it is unclear whether using an ABB or KUKA template introduces offsets or axis conventions that do not apply to the Kawasaki FS45N. RobotDK has a negative 90-degree angle in its robot as the home position. I modeled the robot in Rhino with exact same bend and imported it into Robot's plugin. This is not unusual, of course, as every single other robot seems to have this exact same bend. My question was, does this influence the reliability of Robot's plugin? I also attempted to work with Robot's plugin with this as the default, except the Robot's plugin had axis 5 and 6 completely off. It needs to have this as a starting point to then correctly give motion to joint 5 and 6. I also tested HAL Robotics because its website advertises support for Kawasaki and specifically the FS45N. However, the plugin itself only provides manufacturer options for KUKA, ABB, and UR. Full functionality also requires a license, and the FS45N's default position still appeared inconsistent with the expected Kawasaki 0 position. It was also necessary to deviate from the manual's joint 3 minimum and maximum values because the robot's plugin reported axis 3 errors in positions that should have been valid. There's nothing wrong with this position. Axis 3 is not outside of the permitted range. Although changing the limit to remove those errors, it also raised doubts about the reliability of the plugin's internal kinematics and program output when applied to a Kawasaki robot. For that reason, I avoided relying directly on the robot's program output when building the post-processor. Instead, I used the same target planes supplied to the plugin and converted them independently into Kawasaki AS commands. Based on the AS language manual, the resulting program appears correct. I still needed to determine whether the robot simulation could be trusted for visual verification and error checking. I therefore compared 3 available kinematic results using exactly the same joint values. The robot's program simulation in green, the robot's forward kinematics component in red, and the HAL Robotics forward kinematics component in blue. This is where the problem became more serious. All 3 produced different robot positions. For the robot plugin, flipping the signs of the joint values made the program and the forward kinematics of robots align, except for joint 3, which also required an additional 90-degree offset. This may be related to RobotDK's minus 90-degree joint 3 offset and could indicate that the systems are using different sign and 0 position conventions. To make the HAL Robotics result match the robot's program simulation, I found that joints 1, 4, and 6 required sign inversions. Joint 2 required a minus 90-degree offset, and joint 6 also required a minus 180-degree offset. Some of these changes appear to correspond to the plugin's internal 0 position. For example, when creating a separate kinematics definition in robots, joint 2 requires a minus 90 degrees rotation to match the expected Kawasaki null position. Joint 6 may similarly use a reference position shifted by 180 degrees. The central question is whether these 3 results are actually consistent once the different joint signs, axis directions, and zero position offsets used by each plugin are taken into account, or whether one or more of the kinematics modules is fundamentally incompatible with the Kawasaki FS45N. Now the question is, do you want to use this as the output? You take the robot's output, its program, and you stick it into the push processor, or do you want to take the planes and stick them directly and turn those into the code? The robot should be able to figure out what joint positions are necessary for achieving these planes, correct? And this simulation seems to be accurate enough to mitigate problems. The question is this sufficient? We have a simulation and we have code post process. Does this work? That's the question. Will it output something like this if given to the robot? Of course, we have to define that this is home.